Hello all, I'm Yogesh Singh. Welcome to my YouTube channel, Yogi's Data Lab. So today we are going to talk about logistic regression and we'll talk about supervised learning. What are the two branches in supervised learning and where does logistic regression come into picture? So as you can see, when we talk about supervised learning, there are two types of problem statements. One is a regression problem and another is a classification problem. Now, when I talk about regression problem, I have uploaded the video for linear regression, which I put the link in the description below. You can have a look at it. And when do we use regression? We use regression when my target variable, when my y variable or the target variable is continuous. When I talk about classification, I use a classification problem statement, or I define the problem statement as a classification problem when my target variable is discrete. Here we are going to take a situation where it is a binary classification. Means I have a 0 or a 1. Means a true and a false or a yes or a no. So generally we call 1 as a true or yes, and 0 we generally call as false or no. It can be opposite, it is fine, but this is the positive logic where we say that 1 is a true and 0 is a false. Now, what is the problem statement? What is an example? Let us say that a person will churn out from your network or not. A person will do the payment or not. The transaction is fraudulent or not. Whenever I look into such problem statements, it is known as a classification problem. So since the data set that you are going to get is going to have its independent variables, means the x variables, which is contributing towards your output variable, where the answer is a yes or a no, it means the data set would be something like this. You will have your independent variables here, which we call as the x's, and here you will have your y variable, which will be a 1 or a 0. So I have to predict my target variable, which is ones and zeros. Now let us try to understand how is it differentiating. So if I have to predict ones and zeros, let us say that this is my y-axis and this is my x-axis. I'll have certain values where I have zeros and I'll have certain values which are at 1, which means that this is your 0 and on the y-axis this is 1. Now you cannot have a straight line, something like this, which is justifying all these points. Why is it so? Because if you look at these distances, which are your errors, the more points I have, the more errors I might get. So this is not a very good line which I should go with. Instead, if I try to go with another line, let us say a curve, something like this would justify all the points. So this is not a linear curve, it is a non-linear curve, and it is given the name sigmoid function. Sigmoid function. Now, when I talk about sigmoid function, since this is my x-axis and this is my y-axis, so obviously there is going to be some mathematical equation for this curve. So I can represent sigmoid function as y is equal to 1 upon 1 plus e to the power minus a plus bx. When we solve this, I can say 1 upon y is equal to 1 plus e to the power minus a plus bx. This can again be written as 1 upon y minus 1 is equal to e to the power minus a plus bx, which can further be written as, so 1 minus y upon y is equal to e to the power minus a plus bx. This I can further write as y upon 1 minus y is equal to e to the power a plus bx. Now what do you see here? I have an exponential here. So if I have to bring a plus bx to the base, I will take log to the base e on both the sides. Log to the base e y upon 1 minus y is equal to a plus bx. Now this term is where y is dependent on a single variable x, but it is a linear equation, which we have seen in linear regression already. So if I make this generic, I can say ln, which means natural log, means log to the base e, y upon 1 minus y is equal to beta 0 plus beta 1 x1 up to beta n xn. Now what is my y? These were the values, the actual values 0 and 1. But my probability, whether it is going to be a false case or whether it is going to be a true case, it can be based on probability. I can give a probability or a chance that it is going to be true, it's going to be false. So that probability always ranges between 0 to 1. So I can say that my y-axis is nothing but the probability, which is p. So instead of y, if I write this as ln p by 1 minus p is equal to beta 0 plus beta 1 x1 plus beta 2 x2 up to beta n xn. This equation is the equation for logistic regression, and it is known as logit equation. Logit equation. Now, using this equation, we are going to calculate the probabilities and then we are going to classify them into ones and zeros. But this is what is the equation, which is derived from the sigmoid function, which fits in all the zeros and ones. And why is it called a sigmoid function? It is of the shape S, which fits in all the zeros and ones properly, and hence a sigmoid function for binary classification. Now, let us try to understand this further. Let us say that I have certain actuals, okay, and I have predicted. So I can have zeros, I can have ones. A zero can be predicted as a zero, and a zero can even be predicted as a one. Zero, zero. A one can be predicted as a one, and a one can even be predicted as a zero. Now, this is what was given to me in the data, the actuals. When I built a model and I predicted it, this is what I predicted. So whenever a zero is predicted as a zero, it is known as true negative, which is Tn. So 0 represents a negative, 1 represents a positive. So how do you remember this? 0 to 0 is a true classification, means I have predicted it correctly. And what have I predicted it as a negative? So it is true negative. Similarly, 0 to 1 is a wrong prediction, means it is false. And what have I predicted it? I have predicted it to be positive. So it is false positive, which is Fp. Similarly, this becomes true negative, which is Tn. This also becomes true negative, which is Tn. Now, when a 1 is represented as a 1, this is a correct prediction, right? So it will be true. And what is it represented as? It is represented as a positive. So it is a true positive. So it is Tp. Similarly, this is also a true positive. And this one is a false representation. So it is false. And a 0. So it is negative. And it becomes Fn. These zeros, they are the actual zeros. They are known as n, means the actual number of zeros. And these are the actual number of positives. So it is represented as p. So I can say in a way that the actual number of positives, means p, is equal to the number of true positives plus number of false negatives. In this case, I have two true positives and I have one false negative. So 2 plus 1 is equal to 3. And how many true positives? How many actual positives I have? I have 3 actual positives. So P is equal to TP plus Fn. Similarly, N is equal to Tn plus Fp. Means how many actual negatives are there is the number of true negatives plus the number of false positives. So how many true negatives I have? 1, 2, and 3. I have 3 true negatives plus 1 false positive, which is 4. And how many actual negatives I have? I have 4. So it means that P is equal to Tp plus Fn and N is equal to Tn plus Fp, which tells me that the actual number of positives is the number of true positives plus the number of false negatives. And actual number of negatives is the number of true negatives plus the number of false positives. Now, based on this, there are a couple of matrix that we need to know. The first matrix that we come across is accuracy, which is AC. This is given by the formula Tp plus Tn divided by P plus N. Means the number of true positives plus true negatives divided by the total number of rows. Means how many records we have predicted correctly divided by the total number of records. Then comes another term, which is sensitivity, which is represented by Sn. This is the same thing which is called as a recall, and it is also known as true positive rate, which is TPR. This is given by TP by P, which is TP divided by P is what? It is TP plus Fn. The next term that you will come across is specificity. It is denoted by SP. It is also known as true negative rate or TNR, and it is given by Tn by N, which is Tn divided by Tn plus Fp. The other term that will come is precision, which is represented by PR, and it is given by Tp divided by Tp plus Fp. And the last term is F1, which is 2 multiplied by recall multiplied by precision divided by recall plus precision. So let us go ahead and talk about each of these individual terms. What are these matrix, when to use them, and how to leverage it. So accuracy, as we can all understand, is how many correct predictions are made out of the total number of rows. When I talk about sensitivity and specificity are like brothers and sisters. So these two terms are used parallelly, while recall and precision are again used parallelly. So these two terms are used together and these two terms are used together. Now, when I talk about sensitivity or recall or true positive rate, it tells me that out of all the ones that I had received, out of all the actual ones that I had, how many ones did I predict correctly? So if you look at this, I had 3 ones which were given to me and I predicted 2 ones correctly. It's two positives. So here my recall becomes 2 by 3, which is 0.67. If I talk about accuracy, if you look at this, how many true positives and true negatives? How many true positives we have? We have 2 true positives plus 1, 2, 3. 3 true negatives divided by total number of rows, which is 7. So this is 5 by 7, which is somewhere around 0.7 something, 7170, whatever is the value. So this is somewhere around 0.7. When you talk about true negative rate, what is true negative rate? It is the total number of true negatives divided by the total number of negatives. So how many total negatives I have? I have 4. And how many true negatives I have? I have 3. So it is 3 divided by 4, which is 0.67. 5. When you talk about precision, precision is out of all the positives that I have predicted. Now, when you predict a positive, when you predict a 1, you can either predict it to be a true positive or it is going to be a false positive. Means out of all the positives that I have predicted, how many true positives are there? So if you look at this, how many positives have I predicted? I have predicted 1, 2, and 3 positives, out of which 2 of them are correct. So 2 true positives divided by 2 plus 1, which is 2 by 3, which is again 0.67. When I talk about F1, F1 is a balance between recall and precision. Now, we need to understand why we need a balance and at what point we are going to use this. So whenever you are building a model, the thing is, I need to decide on certain matrix. I can decide on recall, I can decide on F1. Accuracy, we don't use as a matrix in majority of the cases. I'll tell you why accuracy alone is not a very good matrix for a classification problem. But when we talk about recall, when we talk about F1, I have to decide which one I have to concentrate on and when. So let us say you are doing some work on email marketing. You want to predict which of these subscribers or which of these people are going to open the email. Because we know that if they open my email, they subscribe. But the cost of any false positive means I'm telling that the person is going to open the email, but he is not going to open the email. So the cost of me sending emails is not very high, and it is a one-time job that I'm doing. So I'll concentrate more on the recall because my operational expense related to the false positive is very low. However, if you are talking about detecting frauds, let us say, so when there is a fraud, we generally raise an alert. When we raise an alert, there is a team which is sitting there which analyzes the records, or there's a customer care which calls the customer and confirms if the transaction was made. So there is a salary which is associated, which I need to pay to my employees. When I go ahead and have a lot of false positive in this case, what will happen is my operational expense will rise. So I will not want that despite of me making profits, which is more with the true positives, I'm also making losses, which is high because of the false positive. So what will happen is your profits will diminish, or possibly sometimes your false positives is so high that despite of you making profits, you are still going at a net loss. So in this case, when I go into certain situations where my operational expense is high, I'll prefer to use F1 such that I can balance the recall and precision. Now, why there is an imbalance in recall and precision? It is because if my algorithm is learning good from the ones, the pattern is recognized well, it will predict the ones to be ones, which is very good, right? My true positives will increase. If my true positives increase, my recall will also increase. But the problem here is that when the ones start becoming ones, my zeros will also start becoming ones because I have overlearned the ones. Now, when the zeros start becoming ones, my false positives will increase. When my false positives will increase, it means the denominator will increase, my precision will fall. So my precision will fall. So this is always going to be the case that there is either the recall is very high, then the precision will be very low, or you need to balance them. Now, this depends again on the problem statement that we're trying to solve. So we'll have to take a call whether I want to concentrate on this or I want to concentrate on F1. I also said a point that accuracy alone is not a very good matrix. Why is accuracy alone not a very good matrix? So if you look at this, let us say you have 1000 rows of data, out of which you have 950 zeros and you have 50 ones. These are the actuals, okay? Actuals. When I build a model and I predict it, I ended up predicting 950 zeros. I predicted 0 ones. In this case, I ended up predicting 40 zeros and 10 ones. Now, what is this? This is number of true negatives. This is false positive. This is false negative, and this is true positive. So if you look at the accuracy is 950 plus 10 divided by 1000, which is 96% accuracy. But if you look at the recall, you were to identify fraudulent transactions that were your ones. Now, if you look at the recall, how many true positives are there? 10 divided by the number of positives, which is 50, which is 20%, which means that despite your model is 96% accurate, you are able to identify only 20% of the fraudulent transaction. So this is not a very good result. So this is why accuracy is not a very good matrix to look at in a binary classification. You should concentrate more on recall or F1, whichever matrix you have selected. Now, there's another concept which is known as confusion matrix. I've seen many people get confused in this confusion matrix, but this is one of the most simplest things that you can look at. It is nothing but a cross table between the actual and the predicted. See, when I talk about actual, there are two things, 0 and 1, and in predicted, I can have zeros and 1. So in a cross table, what happens? It gives the number of rows. So what am I looking at? The number of rows which were actually 0 and it has been predicted as 0. So I'll get the number of true negatives here. The number of rows which were actually 0 and I predicted them to be 1. So this is false positive, number of records of false positive. Similarly here, number of records of false negative and number of records of true positive. Sometimes people change this. So it depends on how they are making it. Actual 1, 0, predicted 1, 0. So 1 being predicted as a 1, it will be number of true positives. 1 being predicted as a 0, it will be number of false negatives. 0 being predicted as 1, it will be false positives. And 0 being predicted as 0 will be true negatives. So you need to look at the actuals and the predicted, and it is being predicted as what. Based on that, you can go ahead and determine what your confusion matrix is stating. So confusion matrix is a method to identify that once I built a model, how many true positives, false positives, true negatives, and false negatives I am getting in my data set. Now, let's go to the other concept, which is known as receiver operator characteristics. This is known as ROC curves. So ROC curves, we can say that is a concept which is taken from the telecom domain. So if you remember those old cradle phones where we used to pick up the cradle and call before the advent of mobiles, sometimes there used to be calls which used to go to the wrong destination. And still you were charged because the call was still placed, though it went to the wrong place. So this was a concept which was taken from there, which is a plot between true calls and false calls. False calls. When I talk about the true calls and false calls, the curve that we used to get is something like this. So what will anyone want? They will always want that majority of the data should be with the true calls and very less data should be with the false calls. So this was changed when it came into data science, and this changed from true calls and false calls to true positive rate and false positive rate. So this is your TPR and this is your FPR. Now, what is true positive rate? If you go back in the set of formulae that we discussed, true positive rate is nothing but the sensitivity. So I can say that my y-axis is nothing but sensitivity, and x-axis will become 1 minus specificity. Why 1 minus specificity? So if I say, look at the formula of specificity, it is Tn by n, which is true negative rate, right? Let's look at it. See, specificity is true negative rate, which is Tn by n. Now, when I talk about this Tn by n and I do 1 minus specificity, what will I get? I'll get 1 minus Tn by, I'll expand this value of n, which is Tn plus Fp. So this becomes Tn plus Fp minus Tn divided by n. This cancels out and this becomes Fp by n. So how many false positives out of the total number of negatives? So it becomes false positive rate. So my x-axis is 1 minus Sp. The other question which is important to understand here is what is the value of sensitivity and specificity for me to have a 100% accurate model? So let us look at it. So what is sensitivity and what is specificity? So sensitivity is Tp divided by Tp plus Fn. And specificity is Tn divided by Tn plus Fp. For me to have a 100% accurate model, it means that my false negatives should be 0 and my false positives should be 0. When your false negatives and false positives are 0, your sensitivity becomes Tp by Tp, which is 1, and specificity becomes Tn by Tn, which is 1. It means that if I have to get a 100% accurate model without any false positive or any false negative, I should have my sensitivity to be 1 and specificity to be 1. So if I have to plot that on this chart, how will that curve look? So let's have a look. So when I do 1 minus specificity, 1 minus 1 is 0. It means that x-axis is 0 and sensitivity is 1. So let us say that if sensitivity is 1 here, so the best curve that you're going to get is going to be something like this. It's going to be vertical till this point of 1 and then it becomes horizontal. So this is your best ROC curve that you can get. And this one that you see here is the practical ROC curve that you are getting. This is the best one. There's another thing which we have to consider here is, let us say that I have been given two curves. One was this orange one and the other is, let's say, the green one. The orange one represents model M1, means I have built two different models. For the first model, which is the orange one, I have this ROC curve. And for the second model, which I have built, this is the ROC curve. Now, which one of them is a better model? So if I have to look at this, what I'm going to do is, let us say I'll go ahead and draw a line at 45° over here. So if you look at this area, which is enclosed by the green line and the dotted curve, this area is less as compared to the area which is enclosed by the orange line or the orange curve and the dotted line. So this is what we are talking about, area under curve. So when I say that area under the curve for model M1 is greater than area under the curve for model M2, hence model M1 is a better model. Or the other way to think of it is, model M1 is more closer towards the true positive axis and hence model M1 is a better model. So AUC is area under the curve. In the industry, when we are working on this, we generally prefer to have an area under the curve greater than 70%. This is what we try to achieve. So this is all about your ROC curve. Now, let's go back to the basics. So we started from here. We said that we are predicting probability. Now probability will lie between 0 to 1, can be anything, can be 0.00001, can be 0.2146, can be 0.7132. But how do I know based on this probability that I have got that I should represent my output to be a 1 or to be a 0? So we take the simple number system. What we do is anything which is 0.5 and above, we classify that as a 1, which we do in rounding off. Anything which is less than 0.5, we classify it as a 0. So this is your threshold value, 0.5. Anything above this is made as a 1 and anything below this is made as a 0. But this is not a very foolproof method. Why? Because not as a foolproof method, it is more of a, I can get much better recall, I can get much better precision if I shift the threshold from 0.5 to maybe 0.7 or maybe to 0.3. I might get much better results. So that is known as determining the optimal threshold. So let us talk about optimal thresholds. Some people also call the threshold as cutoff. It is entirely on you, whichever word you want to use, both of them are correct. Now there are a couple of methods here. First, it is known as distance cutoff. The second method is KS cutoff. The third method is REPR cutoff or F1 cutoff. Now let us try to understand what are these. Now distance cutoff. For distance cutoff, we will go back to your ROC curve. So I'm talking about distance cutoff. So my y-axis was Sn. My x-axis was 1 minus Sp. I got a curve which is something like this. And this is 1, which we just saw is the best point. Now, if I have to determine the best probability, it means that it has to be some point on this curve which has to be nearest to this point, which has to be nearest to the most optimal point. So I don't know which one of them is this. Maybe it is this distance, maybe this distance, maybe this distance. I don't know which one. But the first thing is I need to calculate this distance. So how do we calculate this distance? So let us say I'll calculate the distance here. I want to calculate the distance of this point with this point. So what I'm going to do is, let's project it downwards. So this distance is 1 minus Sp. When you look at this distance is Sn. So this pending distance will be 1 minus Sn. Since this is 1 minus Sp, this will also be 1 minus Sp. This is a right angle triangle, so this becomes the hypotenuse. So as per Pythagorean theorem or the Pythagoras theorem, whatever you call it, this distance d will be equal to square root of 1 minus Sn whole square plus 1 minus Sp whole square. So the probability where this distance is minimum is known as the distance cutoff, because I want the minimum distance over here. So the probability where d is minimum is distance cutoff. Now the other thing is KS cutoff. KS cutoff stands for Kolmogorov Smirnov cutoff. There's a principle of KS cutoff. Principle of KS cutoff is zeros and ones should have maximum separation. So first, let us look at the mathematics of this, how it is done. So what we do here is, let's say I have 1000 rows of data and I have 700 zeros and I have 300 ones. This is the data that I have. So the first step is predict the probability. Once I have predicted the probability, I'll sort them in descending order. So when I have predicted the probability and I have sorted them in a descending order, it means that you'll see that the higher values which are most probably to be ones, are going to be on the top, and the smaller values, which I'm going to classify as zeros, is going to be at the bottom. So I'm sorting them in a descending order. The third thing is create bins. When I say create bins, it means that if I have 1000 rows, maybe I'll go ahead and create 10 bins, and each bin is going to have 100 rows. So let us see how this works. So I have created my bin. So I have 10 bins, 1, 2, 3, 4, 5, and likewise I'm going till 10. Then I'll count the number of zeros and the number of ones in each bin. Now, since I have sorted the probability, the chances are that I'll have maximum ones on the top in the top bins and maximum zeros in the lower bins. So hypothetically, I'm assuming that I have 0 zeros over here and I have 100 ones in the first bin. In the second one, I have 10 zeros here and I have 90 ones. I have 30 zeros here and I have 70 ones. And then suddenly something flips. This becomes 80 zeros and 20. This becomes 85, 15. And eventually you will see that here you will end up with, let's say, 100 zeros and 0 ones. The next step is to calculate the percentage of zeros and percentage of ones. So 0 divided by 700 is 0 because I have 700 zeros, right? Then you will have 10 divided by 700. So let's say it is 0.01. This is assuming, I'm not calculating anything, I'm just assuming. Let's say this is 0.02, this is 0.13, 0.14, and this will be 100 divided by 700. So let's say it is 0.70 or something. Okay, now in percentage of ones, what will happen? It is 100 divided by 300, which is 0.33. Then you have 90 by 100, which is 90 by 300. So it is 0.30. This becomes 0.27. Let's say this is going to be 0.10. Let's assume this is 0.08. And likewise, this will reduce further to 0. Now I'll calculate the cumulative percentage of zeros and the cumulative percentage of ones. So cumulative percentage of zeros and cumulative percentage of ones. So this is 0. So the first term is 0. So you'll get 0. Then 0 plus 0.01 is 0.01. 0.01 plus 0.02 is 0.03. Then you have 0.16. Then you have 0.30. And likewise, it will go here and it will become 100% because it is cumulative percentage. When I talk about cumulative percentage of ones, we'll start with 0.33. This will become 0.63. This is 0.63 plus 0.27. It will be 0.90. So this cannot be 0.10. It has to be something different because it will end up with 100%. So let us say this is 0. I'll change this. Let us say this is 0.08, 0.05, and so on. So this becomes 0.98, 0.02, let's say, and then everything becomes 0. This becomes 1.00, and gradually it will be going to 1.00. Now, what I have seen here is I have got the cumulative percentage of zeros and cumulative percentage of ones. So I'll go ahead and calculate the difference. The difference is cumulative percentage of ones minus cumulative percentage of zeros. So this is 0.33. This is 0.62. This is 0.87. This will be how much? 0.82. This will be 0.70 and gradually it will go down. Now, if you look at this, if I look at the maximum difference in this column, where do I have the maximum difference? I have it here. It means that my zeros and ones are separated with a maximum distance at this point. So the probability at 300th row is KS cutoff. Why 300th row? Because every bin has 100 rows. So 100 here, 100 here, 100 here. So I end up with 300 rows, and the probability at the 300th row is the KS cutoff. This is the mathematical way of understanding this. However, if you have to solve it using Python or R, and the much easier way of doing it is calculate the difference of TPR minus FPR, the true positive rate minus the false positive rate. Take an absolute of this and the point or the probability where this value is maximum is known as the KS cutoff. So this is your Kolmogorov-Smirnov cutoff. Let us try to understand the third one, which is the REPR cutoff. In REPR cutoff, what happens is, let's say this is my probability. As we all know, when my recall increases, my precision decreases. So the point where they intersect, that probability is known as the REPR cutoff. This probability is the REPR cutoff. But the problem with this is you have to manually go ahead and look at this curve and identify it. A much easier way is, since it is a harmonic mean, F1 is a harmonic mean of recall and precision. So this is the point where F1 will be maximum. So I can do is the probability where F1 is maximum is F1 cutoff. So the result that you are going to get with F1 cutoff or the REPR cutoff, both are going to be the same. So whichever you are comfortable with, you can use this or you can use this. Now the last topic that we are going to talk about is concordance. When I talk about concordance, I don't see people using much these days, but it used to be a good matrix. Now concordance believes in two things. Number one, probability of ones should be greater than probability of zeros. This is the basic thing which it believes in. The second thing is about concordances, it does not believe in cutoffs or threshold. So how does this work? So let us try to understand. Let's say this is my row number, means my data. I have row number 1, 2, 3, 4, 5, and 6. This is my actual data. I have 0, 0, 1, 1, 0, 0. This is the data that I have. I'll predict the probability. So let's say this 0 got 0.01, this got 0.90, this got 0.90, this got 0.98, this got 0.21, this got 0.04. This is the probability which was predicted. Now when concordance starts working, what it does is it first creates the pairs of ones and zeros. So let's write here ones and write here zeros. So the pairs that are going to be created is row number 3 with row number 1, 3, 1, 3 with 2, 3, 2. Then you have 3 with 5 and 3 with 6. So you have 3 with 5 and 3 with 6. The next set of pairs will be 4 with 1, 4 with 2, 4 with 5, and 4 with 6. So let's write it 4, 1, 4, 2, 4, 5, and 4, 6. So these are the pairs which will be created. Once the pairs are created, what it is going to do is it is going to check if the probability of ones is greater than the probabilities of 0. So 0.90 is greater than 0.01. Good. Here 0.90 is equal to 0.90. Then 0.90 is greater than 0.21. 90 is greater than 0.21. Then I have 0.90 is greater than 0.04. Then I have 0.98. 0.98 is greater than 0.01. 0.98 is greater than 0.90. 0.98 is greater than 0.21, and 0.98 is greater than 0.04. So whenever the probability of 1 is greater than the probability of 0, it is called as a concordant pair. Concordant pair. When both the probabilities are equal, it is known as a tie pair. So this is concordant, this is concordant, 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 and concordant. In case the probability of 1 is less than the probability of 0, if probability of 1 is less than probability of 0, let us say, then it is known as a disconcordant pair. In our case, we see that we are only concordant and tie pairs. Now, once you have calculated the concordant and the tie pair, what we are going to look at is we are going to calculate the percentage of concordance. So how many concordant pairs we have? 1, 2, 3, 4, 5, 6, 7. We have 7 concordant pairs out of 8 pairs. So if I have 7 concordant pairs out of 8 pairs, what is the percentage of this? 7 by 8 multiplied by 100. So 2, 5, let's do the multiplication. 2. So whatever is the percentage, you get 8 and you get 87.5. 87.5%. So whenever I'm getting 87.5% over here, it means that the model is good. So in the industry, when this concept was being used, we used to say that if you're getting a concordance percentage of greater than 80%, it means that the model is an acceptable model. So this is all the theory that we have for logistic regression. Now, let us start with the case study. So here you can see on the screen that we have to figure out which customer is most likely to default. The data that you have been given is the customer ID, status checking account, duration in months, credit history, purpose credit taken, the credit amount, savings account, years at the present employment, interest rate on income, marital status gender, other debtors, guarantors, current address years, property, age, other installment plans, housing type, number of credit cards, job, dependents, telephone means the type of phone number provided, foreign worker, and default on payment. Now this is our target variable. So we'll start working towards this. So we'll start importing the libraries where you see that we have used the train test split, we are using logistic regression, we are using sklearn matrix for all the matrix that we are going to use like recall, precision, F1. And now I'll read my data set. After reading the data file, I'll look at the head and it shows that I have my customer ID, I have my other columns. The data seems to be pretty clean. The column names are clean. And my target variable, which is the default on payment, which is in zeros and ones. I'll check the shape. It shows me I have 5,000 rows and I have 22 columns. These are my column names, which I have seen, and they seem to be pretty clean. I don't need to clean them. I'll drop customer ID because ID is something which is not going to contribute towards my target variable, based on which any specific customer ID is not going to contribute whether the person is going to default on payment or the person is not going to default on payment. So I'm going to drop the customer ID. I'll correct my spelling of purpose credit taken. It seems to be wrong, so I'm correcting this. I'll replace any spaces if in the column names with no space. And this is the final data which I'm getting. When I look at the info, it shows me that I have no missing values. I have 8 integer and 13 object columns. Number of unique values, when I'm looking at, I don't see any zero variance column, which is good. Number of missing values, I don't see any missing values. When you look at the description, what does it show you? It shows you on an average, the credit amount that is taken is 3,271, which is more than the median, which is 2,319, which means that the data is skewed towards the right. The duration is also slightly skewed towards the right because the mean is greater than the median. Interest rate is approximately same, so which is fine. Current address years is also approximately same. Age is very slightly skewed towards the right with a minimum of 19 years and a maximum of 75 years. Number of credit cards, on an average, people have one credit card ranging from 1 to 4. Dependents, one dependent with a minimum of one dependent and a maximum of two dependents. Then when I look at the default on payment, I have around 29.9% of ones and the remaining are zero. So I have plenty of ones in my data. Then you will look at the categorical values. So you see that there are all the values are encrypted over here. They are masked with different values. So we won't understand much over here. So you can't do much about this. Now I'll go ahead and look at the histograms. So a couple of them seem to be skewed, like default on payment, current address in years is skewed slightly towards the left, age is skewed towards the right, duration in months is skewed towards the right, credit amount is skewed towards the right, but we'll leave them as it is for now. Let us build a model and see how the results are. I did not do the EDA here in detail because I didn't want to make the video lengthy. You can go ahead and certainly do the EDA for your using a univariate, bivariate and multivariate for all your numerical columns and categorical columns and try to understand the pattern. Here I'm just replicating or trying to show you how logistic regression works. So I didn't do much into the EDA part over here. So here I am converting the objects into categories, which you can see has been converted here. The reason why we convert object into category is the data size becomes manageable. It becomes a bit smaller and the processing becomes a bit faster when you're handling it in category rather than using an object. So this was a basic part which we do in every machine learning problem. Now let us concentrate more on the model building. So when I look at the model building, what I've done is I have dropped my default on payment, which is my target variable, and I've created my independent data set. And I have created my dependent data set, which is Y, which is the default on payment. Now for the independent data set, I am creating my dummies. And using these dummies, I am going to go ahead and create my train and test data set. So I'm doing a train test split. 70% goes into train and 30% goes into test. I'm using a random state of 5, means I'm setting a seed of 5 over here. Now I'm creating an object of logistic regression and I am fitting it on the train set. And this is what is I have to do for logistic regression. My model is done. Once this model is built, once I have done my logistic regression over here, I'll use a default threshold or a default cutoff of 0.5. If you remember the sigmoid function, in the sigmoid function, we have values at 0, we have values at 1, and we are going with the threshold of 0.5. Means anything greater than equal to 0.5 becomes a 1, anything less than that becomes a 0. So I am doing a logreg.predict. Logreg is your model name over here. And since the model is already ready, I am doing a dot predict on the train set. Similar to what we did before in linear regression, I am predicting on the train set from which I learn to see exactly how the results are. So if I do logreg.predict on the train set, I have got my predicted values in pred train. Now I'll create a confusion matrix. Now what was a confusion matrix? A confusion matrix is nothing but a cross table between the actual and the predicted values. So I'm giving a confusion matrix with my actual values, which is y train, and pred train, which is my predicted values. So you can write it in a way, let me write it. So you'll get it something similar to this as actual and you will have zeros and ones, and it is you have predicted, and you have 0 and you have 1. Now these values that you are seeing here, this 2240, this 2240 is coming here. This is, let me write it here, 2240. Then you have 237 over here. So you can say this is here. Then for ones you have 575 here, and you have 448 here. So what it means is, whenever your actuals were zeros and you predicted it to be zeros, these are the count, means these are the count of true negatives. When you talk about this, this is actually 0 and predicted 1. So these are the count of false positives. These are actual ones and predicted zeros. So these are the count of false negatives. An actual 1 and predicted 1. So these are the count of true positives. So this that you see over here is giving you that matrix of the actual being predicted as actual 0 being predicted as 0 means true negatives. Actual 0 being predicted as 1 means false positives. Actual 1 being predicted as 0 means false negative, and actual 1 being predicted as 1, which is true positive. So, well, this is what I got in the confusion matrix. Now I'll do it on the test set. So on the test set, I am getting similar, these many true negatives, these many false positives, these many false negatives, and these many true positives. Now, since I've got my confusion matrix, I have built a model, I've predicted on my train set, on my test set, I will go ahead and compare the accuracy, recall, precision, and F1. So there are commands which you can use, like accuracy score for getting your accuracy, recall score for getting your recall, precision score for getting your precision, and F1 score for getting your F1. You need to give the inputs as your actual value and the predicted value. So here I am giving the actual value of train and the predicted value of train. Here I am giving the actual value of test and the predicted value of test. Similarly, I'll do it for recall, precision, and F1. I have given the similar results. And if you look at this, I was concentrating on the recall here, trying to identify how many defaulters am I able to predict. And I see that the results are pretty poor, 43 or 44% on an average, approximately rounded off. You can say that the recall on the train set is 44% and the recall on the test set is 43. The model is not overfitting because the difference between the train and test is within 2%, but the recall value is very low. This is something which is not really good and I need to improve on this. So let us go ahead, let us try to see more things. So I'll go ahead and plot a ROC AUC curve, your receiver operator characteristics. So here I am doing it on the test set. I give my Y test and I'm using log reg dot predict proba. When you do predict proba at this point, what it does is it predicts the probability. So see here what we did in this case. When I did predict, it was by default taking a threshold of 0.5. I don't want 0.5. I want the probabilities here, right? So what I'll do is instead of using predict, I'll use predict underscore proba. So when I'm using predict underscore proba, what it is doing is it is predicting me the probability on the test set. But when it does so, what it will do is it will also, when you use this and you print this somewhere just prior to this code, you'll see you'll have a column 0 and a column 1. Column 0 means the probability of the occurrence of 0 and column 1 means the probability of occurrence of 1. Now there are only two things that can happen. A 0 can happen and a 1 can happen. So the probability of the occurrence of 0 is 0.90. The probability of occurrence of 1 will become 0.10, means 1 minus 0.90 is 0.10. I want the probability of the occurrence of ones, and that is why you'll see I have taken 1 over here. This represents all the rows and this is the column 1. Now this will give me the ROC AUC. I am looking at the ROC curve. Similarly, I am giving my values over here, and this is all that I need to change in this code. Rest everything is pretty standard. And when you look at this, this is what you will see. You will see this is your ROC curve, how it looks like. And the area under the curve comes out to be 80%. So generally we go with an area under the curve as 70%. Here we are getting 80%, which means I'm doing a decent job. Despite that, I know that my recall is really not that good. So what can I do now? So what I'll do is I'll go for optimal cutoff or optimal threshold. So as we discussed in the theory part, there were a couple of methods where out of which we discussed the distance method, distance cutoff. We talked about KS cutoff or Kolmogorov Smirnov cutoff. We also talked about REPR cutoff or the F1 cutoff. So we are going to use these now and try to see how it impacts my results. So here, when you look at this, I am predicting the probability on the train set. So this is how it will look. It means for the first record, the probability that it is going to be a 1 or the output is going to be a 1 is 0.4559. For the second record, the probability that the output is going to be a 1 is 0.4264. For the last record, the probability that it is going to be a 1 is 0.9275. So this is what is the probability that is being predicted for my train set. Now I'll create a cutoff matrix. I have to use these values to come up with the optimal threshold. So what I'm doing is I'm creating a data frame eventually where I'll have these column names: cutoff probability, true positives, false negatives, true negatives, false positives, actual number of positives, and actual number of negatives. So I'm creating a data frame with this column names, and I'm creating a range from 0 to 1.00 with a gap of 0.01. Since I'm using a range, hence I have given it 1.01 so that it creates the values up to 1.00. Now, the concept here is whenever my cutoff probability, this thing, I'll compare the actual predicted probability, which I got here, this one, with the cutoff probability. And if it is greater than the cutoff probability, like the case where we were taking 0.5 and anything greater than 0.5 was 1, anything below was 0. Similarly, let's say I assume that my cutoff probability eventually in a loop is coming to be 0.2. So anything greater than 0.2 will be 1 and anything greater than 0.2 will be, anything smaller than 0.2 will be 0. Similarly, at certain point, it will move on, the loop will move on, it will come to 0.70. Anything greater than 0.7 will become 1, and anything less than 0.7 will become 0. So what I'm doing is I am moving the cutoff probability from a scale of 0 to a scale of 1. 0, 0.01, 0.02, 0.03, and at every point, I am saying that assume this to be a cutoff. Now, anything greater than these points, whatever I'm assuming, becomes a 1. Otherwise, it becomes a 0. And whenever my ones and zeros keep on changing, my true positives, false negatives, true negatives, and false negatives will also change. Now, since my TP, FN, TN, and FP are also changing, my recall, my precision, my F1, everything changes. And this is what I'm trying to achieve here. So here in a loop, when the cutoff is 0.00, if my predicted probability is greater than 0.00, convert that into, this will be a true and a false, convert that into an integer. So whenever my predicted value is a 1 and my actual is a 1, sum up all such values and put it in true positive. Similarly, when the predicted is 0 and the actual is 1, it means it is a false negative. Sum up all such values and put it in false negative. Likewise, you'll get your true negative and false positive. P, which is the actual number of positives, is equal to the number of true positives plus number of false negatives. N, which is the actual number of negatives, is equal to the number of true negatives plus number of false positives. Now I am going to use all these values that are calculated. Let us say the beginning is 0.00. So at 0.00, what is the value of TP, FN, TN, FP, P, and N? This loop will go now and become 0.01 because you see here we are increasing this by 0.01. Now at 0.01, what is the TP, FN, TN, FP, PNN? At 0.02, what is the TP, FN, TN, FP, PNN? And this will keep on repeating till 1.00, where I'll find out the TP, FN, TN, FP, PNN. So this will eventually give me a matrix, something like this. So I've taken a head of the cutoff matrix that we have developed, and see at cutoff probability 0, 0, because every probability is going to be greater than 0. So everything will be marked as a 1. When everything will be marked as a 1, it means the actual zeros have been marked as 1s and actual 1s have also been marked as 1. So at a cutoff probability of 0.00, you will only get true positives and false positives. So this is what you see. You get only true positives and you only get false positives. At 0.01, you'll get different values, and eventually you see that your true negatives have started increasing. Now, since I have built this matrix, I can now calculate the value of sensitivity, specificity, distance, Ks, recall, precision, true positive rate, false positive rate, and my F1. So all of are these matrix which we covered in the theory part, and this is what I am putting it here. Based on this, you'll see that you have got all your matrix over here. Now, if I have to select any cutoff, when we talk about distance cutoff, talk about that whenever the distance is minimum, the corresponding probability is my distance cutoff. Whenever my Ks is maximum, then the corresponding probability is my Ks cutoff. Whenever my F1 is maximum, the corresponding probability is my F1 cutoff or REPR cutoff. So here I'm doing the same thing, picking up the minimum distance, picking up the maximum Ks, you see here, maximum Ks or the maximum F1. When you look at the probabilities now, you see that your distance threshold comes out to be 0.23. Your Ks threshold comes out to be 0.21 and F1 comes out to be 0.21. Now I've saved these three, the distance cutoff, Ks cutoff, and F1 cutoff in a list over here. And I am predicting on my train and test whenever it is greater than the cutoff. Means whenever first time greater than distance cutoff, second time greater than Ks cutoff, and third time greater than F1 cutoff. And I'll calculate the accuracy, recall, precision, and F1. So you can see here that whenever I am using distance cutoff, my recall is coming out to be 0.82 on train and 0.81 on test. Now you can see here the importance of a cutoff. At a base threshold of 0.5, we were seeing it was giving a result of 43 and 42, if I remember it correctly. But the moment I used the distance threshold, my recall shifted from 43% directly to 82%. So it's a huge, huge jump just by shifting the threshold and not rebuilding the model. The model is already built. I'm just shifting the threshold. I'm shifting the probability with which I can get these results. So when you look into this, here with the recall, I am getting 0.82 and 0.81. When I'm using your Ks threshold or your F1 threshold, because both of them had the same value this time, I see the recall on train is approximately 85% and that on test is 86% approximately. So it is even much better, and they are not overfit either. They are within a gap of 2%. So I am doing a decent model in terms of recall. So this was the importance of selecting a threshold. Now, we talked about the threshold. We said that we are not going to talk about accuracy. Remember, we discussed why accuracy is not the best measure. So we are concentrating on the recall in this case. The last concept that we covered was concordance. Now, in concordance, this is a function I've created. You can use this, which is to calculate the concordance, where we said that it will pair with a 0 will pair with a 1, and then it will compare whether the probability of 1 is greater than the probability of 0. So I am going ahead and passing the values over here for my data set. And what it does is, you see that it is showing you that the concordance percentage is 81.22. So as I told in the theory part that we generally accept a model if the concordance is greater than 80%. So in nutshell, what you saw is, you saw that we built a Bayes logistic regression model with sklearn. We tried it with a threshold of 0.5, which gave me a very poor recall. Then we tried optimal threshold methods. We tried distance cutoff, we tried Ks and F1. And we got the best results with KS threshold, which was 0.21. And the recall, which we were getting as 43 at 0.5, eventually increased to somewhere around 85, 86 with the KS threshold of 0.21. Then we also looked at the ROC curve, AUC curve, where we saw that we are getting the area under the curve as 80%. So it's a decent model. Along with that, we also saw that the concordance percentage is 81% over here. And hence, all these indicators do show me that I have a decent model and I can go ahead with this model. So this is all we have for the case study. So if you did enjoy this video, you did learn something more from this video, please do like, share, and subscribe, and see you in the next video. Thank you, everyone.